Hey. Alright, so let's talk about Mercury. Mercury is the closest planet to the Sun, and as we can see here on eyes in the solar system, let me get rid of spacecraft. Here we got Earth and the Sun, and Mercury is the closest to the Sun. So, because it's closer to the Sun than us, it has an inferior orbit. It only gets a certain distance away from the Sun in the sky. Over here you see this is the Moon, Venus, Mars. You can see the Sun has already set, and Mercury is not far behind. In fact, if you've already done the Mercury lab, you know that it only gets 28 degrees away from the Sun. And what that means is, like, let's say the Sun is maybe here. If you can see that, the Sun's maybe here. Then 28 degrees is really just a length on the sky. But in space, it's this angle. You got the Sun here, Mercury in this direction, and the angle between those two lines is 28. So on here, if you point your finger straight at the Sun, that's like pointing along this line. Then if you point your finger straight at Mercury, that's like pointing your finger straight on this line. Then the angle between those two lines is 28. What does that look like from Earth? Well, let's go into Earth. And if we let's see, I want to go the other way. The Earth's upside down. Ah, whoa! What's going on? Earthquakes, craziness. Ah. Okay, that's pretty good. So this is real time and now. You can see Mercury is actually just about as far away from the Sun as it's going to get in its orbit. I'll leave the orbit on for a little while, but then I'll take the orbit off and you can see the difference. But if I speed things up, now Earth is spinning really fast. You can see Mercury's getting closer to the Sun. If I pause it, that's less than 28 degrees. And as time goes on, it's going to get even less. Let's just watch that for a little bit. Now Mercury is right on the Sun, and now past it, right? Let's take off orbital paths. And we can maybe see that a little better. See the Moon zip by. The Moon goes around about once every month and often passes right near Mercury. So Mercury's getting closer to the Sun, closer to the Sun. And if you notice, if you remember last time when we started it, Mercury's orbit seemed to go farther on this side than it did on this side. It's because Mercury has a pretty eccentric orbit. So it's getting farther. I'm not going to make you dizzy by tilting anymore, but you can see still getting farther. It might just be starting to turn around now. Yeah, in fact you can see it starting to slow down and go backwards. Whoa. So that's pretty cool. Back to now. So if you want to see Mercury, you really have to be you have to pick your time wisely. It has to be far enough away from the Sun so that it's not dominated by sunlight, and the Sun most likely has to have set or not risen yet in the morning, and then you might be able to see it. Orbital properties. So Mercury has some weird orbital properties. It rotates once every 59 Earth days, so a day on Mercury is pretty long. Not only that, since it's so close to the Sun, it only goes around once every 88 days. And if you do the math, 55 and 88 are make a nice pattern. It basically means that Mercury rotates exactly three times every 2 orbits around the Sun. So if we go back to Earth, you know that Earth rotates once a day, and it takes 365 days to go around the Sun. So if we speed things up, oh, let's turn it this way. Okay. If we speed things up, you can see that Earth spins spins around a lot for just a little bit of orbit. See, the sun's not moving very much, which means it's taking a long time for Earth to orbit around the sun at this, even at this speed. But look how quickly the Earth is spinning. Let's see what it looks like for Mercury. Speed things up. Look at that. The sun's zooming and Mercury's hardly spinning. If we try to keep the sun in view here, the sun's zipping around and Mercury's barely spinning. So this shows you the following. You know, one day on Earth, that's gross. One day on Earth, 365 days per year. That's tiny. 59 days on Mercury compared to 88 days to go around the sun once. Sorry, I'm not saying that very clearly. One day to rotate once, 365 days to go around the sun once. And that's a tiny fraction. If you do 1 divided by 365, it's a tiny number. 59 days to spin around once, to rotate once, 88 days to go around the sun once. If you do that, that's a much larger number. 60 over 88, that's between 1.5. So you got 0.5. It's greater than that. But less than 1. So, and that's the value of this fraction here. So, anyway, I'm just trying to prove a little mathematically that Mercury doesn't rotate very quickly for the number of times it goes around the sun. If you look at this little picture here, you can also see that. You might want to pause it to take a look at what's going on, because I'm going to switch slides pretty quickly. But this is another way of looking at it. You can see here, this is the orbit around the sun, and we start here at day 0. 15 days later, Mercury's here, and then 59 days later, Mercury has rotated once completely around. That's 1 day of Mercury. It takes this long and this much of its orbit to spin around once. And then, of course, it takes 88 days to make it around the sun once. So that's what you see here. Day 88. You can see 59, 60, 74, 75, 76, 77, 77, 80, 81, 82, 83, 45, 86, 87, 88. And then it continues on here, 89, 90, 91, and so on. Just like that. So take a look at this and see if you can figure out what's going on there. Mercury's rotation axis is not tilted like the Earth's. So one last time on eyes, let's try to find Earth again. And I'm going to bring back the orbital paths, orbital lines. Let's find the sun. Let's straighten this out. There we go. That's pretty good. Now here's the plane of the solar system, also the plane of Earth's orbit, and watch the spin rate, or watch the spin angle. See how it's down like that? Remember, it's like 23 plus degrees. So you can see that the Earth's axis is tilted with relation to the plane of the solar system. Let's check Mars out. Same deal. We just learned about that. Where's Mars? There's Mars. Yeah. Alright, let's play. And you can see what's cool about Mars is the moons are also tilted the same way as the rotation axis. So you can see here's the plane of the solar system, and here's the plane of Mars's rotation axis, and it's tilted by that many degrees. If I were to draw like, whoops, line here, where'd you go, eyes? And then a line here. See that? This angle here is 23 something degrees. But if we go to Mercury, Mercury, where are you? And do the same thing, you can see that even though it's rotating much more slowly, still you can see that the orbital axis is perpendicular to the plane, or in other words, the plane of Mercury's orbital, the plane of Mercury's rotational axis, rotational spin, is parallel to the orbital plane. What that means is that the sun is directly overhead at the equator at all times. So if you're standing on the equator of Mercury, which is like here, here's the equator. Let me slow this down a little bit. If you're standing on the equator, then which is like here, then the sun is straight up. If you're on the pole, here's a pole, I believe, right? Let's see. Yeah, this is about the pole. Then the sun is always on the horizon. I don't know if can't really see that very well from eyes. But what that means is that temperatures are really hot at the equator because the sun is beaming down directly. Whereas when you're up at high latitudes, especially at the poles, you get very indirect sunlight, which you can see right now. See how that angle is very indirect? And what that means is if any water happened to have come onto Mercury, maybe from a comet or a watery asteroid hitting it, like you saw there, then parts of a crater would permanently be in shadow because the sunlight is always at a low angle. Unlike on Earth and Mars, where it's tilted, so you get seasons and you get different degrees of intensity of light. Mercury, the sunlight is always at the same angle, and so you get parts of craters that are always in shadow. And so it's thought that maybe frozen water could have survived long periods of time on Mercury. Let's stop this video here, and I'll continue with physical properties in the next video. Just before I close, look how close Mercury and the Moon look to each other. They're similar in a lot of ways, yet different in a lot of ways. But if you take just a look at the snapshots of the two, you're like, oh, they could be kind of the same thing. A little deceiving. They're not the same size, so don't let that confuse you. But anyway, we'll talk about that in the next video. See you later.